Alright, so I think we're back. Hello again. We're got another problem. Give me just one moment to get it going. So this one is... haven't looked at it yet. Give me just a moment. Range Edition on Leetcode. Let's see it. What does it say? You are given an integer length and an array updates, where updates of I is start index, end index, increment sub 1. Sub I or sub 1? Let me see. I can't really see. I think it's increment sub I. Okay. So integer length and an array updates. Okay. It's an array of updates. And so it's an array of arrays, right? A vector of vectors. Okay. And in each vector we expect 3 numbers, a start index, an end index, and an increment value. Okay, I think this is going to be, excuse me, a, what do you call that? A interval, what do you call that? What's it called? Interval tree question? Yeah, I think this is going to be an interval tree question. Have an array of length with all zeros, and you have some operation to apply on array. In the ith operation, you should increment all the elements, start index plus 1, end index sub I, sub 1, or sub I rather, index sub I, by increment sub I. You know, by the way, these could just be like ABC, right? Each one is going to have these numbers. Doesn't necessarily need to be, right? Like the index sub I, the I index here kind of implies that these are sort of indexed. So you don't really need to have those subscripts, but anyway. That's kind of beside the point. So return array after applying all the updates. So yeah, what you can do. The problem with this though, okay. Alright. There are a few things to think about. So this is like an interval tree. The problem that you have is, so I want to check something before we keep going. Just give me one moment. So the problem we have with this question is, like, I don't know if there's really, no, wait, let me think. Let me think about it. Yeah, I want to say we should use an interval tree still. So there's like a lot of different thoughts I'm having here. So I'm trying to figure out where to start, where to even begin talking about it. Okay. If you just brute force this, it will be slow. Right, that'll be the slowest case. Now it can be done. You could just brute force this. It looks like the number of updates is relatively small, and well, actually no. This I don't think you could brute force this, believe it or not. Excuse me. All right, 10 to the 5th times 10 to the 4th is 10 to the 9th, which is a billion operations, which is actually going to be too slow, I think. So for the runtime. So actually, no, you do need to be clever about this. So an interval tree is probably the only way to go. Okay. The reason why I was thinking I don't want to use an interval tree is because the updates themselves could be kind of awkward, I guess. But it actually doesn't matter, I think. I think all you got to do is I don't remember if an interval tree will actually modify all of the values. So that's the thing we're trying to avoid. We're trying to avoid modifying all of the array values with each query. Excuse me, we'll call them queries, each update. We can modify the tree, no problem. That shouldn't be an issue. However, we have to be clever about how we do this with our tree. We basically want to say we could do it this way. We could say the interval tree is basically going to be like the values in the interval tree are going to be modifiers. There's actually a way. I don't want to do that though. Something kind of more involved, like a more advanced usage of an interval tree is technically at each node you can store like the actual section of the array at that node. And but that kind of defeats the purpose if we like at each increment we actually do modify that whole section of the array. Like that seems kind of silly, kind of pointless. Well, how do we want to do this where it's still kind of relatively efficient? I want to say something like you can basically the nodes of the interval tree would be like quote unquote modifiers, and so if you increment a section of the tree there would be like a few different nodes. Let me see if I can do this with a picture. Let's just do like something like this. And then we'll do one more at the bottom. So we have another 8. So if we had a 8-node array to operate on, and their sort of initial state is all zeros, and we would say like, okay, this modifier has a -1 on this side here, and then this modifier would have like +1, right? And that would be sort of like the first update query might just be these 2 nodes, this range, and the first one might be these 4, and the second one might be these 2. And what I want to do is like basically your interval tree. You can find a number of nodes that you would want to apply to like grab the whole range, and then those nodes themselves you would add that value. So let's say we wanted this range, right? Let's say we wanted these values. We wanted our update was on these 4, and we wanted to add it was on these 4, and we wanted to add a modifier of like +2. So we would end up with these 2 nodes, or rather, no, actually it's these 2 nodes, and we do +2 on both of those. Whatever modifier was on those previously, I have a +2. And the idea, I guess, would be that once you've kind of processed all of the modifications on these nodes, these modifying nodes, right? You sort of modify. You update the modification of each of those nodes, which sort of represent the underlying array. Then I guess what you would do is you would actually just take each node one by one and just trace the tree down through each node, right? And apply all the auto modifiers as you go. Oops. Yeah. And that's how you would read off the final result. I hope that makes sense. That's what I'm thinking. That's what I'm thinking how to do this. I think you can do it that way. I think you can modify the nodes of the interval tree that represent that particular range. Increment and decrement those nodes. And then when you're done, you can read off each value from the interval tree relatively efficiently. It'll be n log n time, but as long as it's not too large, the array. Well, it's logarithmic with respect to the array size. It's really not too expensive. So the whole runtime would be n log n altogether. It'd be logarithmic. Each update query would be logarithmic with respect to n, and then reading off at the end would be n log n. So this would be efficient. This would work. So we'll use an interval tree. Now I have to remember how to build an interval tree now, which of course I don't remember. Of course I don't remember. I don't know. I don't know. And by the way, we're not going to modify these at all. These are going to be const. Yeah, so, okay. How do we build an interval tree again? How do we do that? What do we do? What? Well, we could use a node class. We'd start with a node struct, inner class, and we could start with that, and you'll have a node pointer. There's the left and the right child, which are both null pointers initially, and then there's a value modifier. Starts off at 0, and we would say to build the interval tree, I'll just write this auto build tree recursively. I don't really know how this is going to work. Node pointer, and we're going to not build this on. Actually, I don't know. I don't know if it really matters. I think we can build this on the heap. I have to destroy this. We would want to use a class. Yeah. We want some things here. Nah, let's make it all public, it's fine. Just want the destructor to work properly, I think. Okay. That's something. We want so this will recursively delete the tree. That's the only thing we need. Right, when you delete the, yeah, okay. Build tree, we're going to, how does this work? We have a length, let's use an int, n, let's say. And obviously we're gonna recursive. So I don't know how you build it. There's a head node, certainly. Okay, that's fine. Also interesting or unusual or weird is that I think there's a way to build an interval tree directly into an array, which is awesome, but I don't know about that. Actually, we should do that. That's better. Yeah, there was a way we did that. We did that before. That's better than doing this. All this extra work. I think what I was just about to do is a little bit. Yeah, you know, we'll do it this way first, so that way I like can grasp what we're doing, right? And then we're gonna try to do this into just a single array, single vector. Give that a shot next. So, yeah. So this is definitely a little weird, a little strange. Also, I'm speaking a lot louder than I thought I would, so I'm gonna just lower the volume a bit. I feel like I feel like I'm speaking really loudly so that people can hear me, but meanwhile, like I'm just yelling into the mic, and it's just too loud. So yeah, so okay. There's a range that you're going to represent. I think that's what I've got to do. Actually, I mean, I'm not sure it really matters. We can do n is greater than 0. Then we'll say node pointer root equals new node root val equals 0, or the modifier is 0. We're going to say left equals f, right equals f, n divided by 2, also n divided by 2. Yeah, see, that's a good question. It would be how many elements? Left. Let's say there's 9 nodes, right? Let's say just thinking how to do this. We could add an extra node to the left side, I suppose. I don't know. Because n is not necessarily going to be a power of 2 minus 1. It could be anything. Just thinking how to do this. Like, you could use a range. Okay, let's do it this way. N minus minus, and we gotta operate on the left side and the right side. So n over 2 and mod 2. Yeah, I guess we'll make the left side heavier then. So more nodes on the left side. So if we did like 8, then we have 7 nodes left. So 4 of them will go on the left, and 3 of them will go on the right. And yes, n mod 2. So 7 mod 2 is 1. If it's even on both sides, it doesn't matter, but on the left, so we'll be left side heavy, right? That's fine, I think that's okay. Okay, create the root node, build the tree. That's pretty simple. And then what we should see is That's it, right? That's like, I'm sorry. That's like, I'm thinking about it. Like, what is this? What happens here? So build a tree. That's fine. Now we want to have update. It's going to do something. There's an update and then retrieve element. I got a few different routines to write here. Right. Okay, hopefully this makes sense what we're doing. So the update is going to modify the tree, and retrieving the element is, and by the way, we also want to delete the head at the end, and then return ret. We'll say there's going to be, we'll make a excuse me, wow, that was kind of intense for a sneeze. Okay. We want to retrieve an element at an index, and we want to create our return vector of ints, and we're gonna build the tree. Then we're gonna process each update. The updates are going to be, this is out of order. So is that one? And this is sort of like a top-down programming approach where you kind of know somewhat what functions you're going to use already, and then so the update is going to take, and let's say int modifier or val, or yeah, mod modifier, and retrieve element is just going to be index, and this we get to, and that's kind of interesting. We could do yeah, I'm gonna drop through the tree. Just thinking how to do this. I'm wondering if I want to add the range that that node specifies. That way it's really easy to do the retrieving of the elements, as opposed to like trying to, what do they call it, intrinsically determine or implicitly determine which node we should be using for that index. So the first node we're always going to use, and then is it the left or the right? That depends if we're less than or greater than, I guess, n over 2. I kind of want to write in the begin index and end index. I feel like we don't need that though. Like I want to say, we said we're going to include on the left side this element if it's odd. So that means that the left side will be inclusive of odd values. Yeah. This is going to be interesting. I don't know. We should be okay. I think we'll be okay with the retrieve element, but that's a pretty interesting kind of approach. And then, or kind of that's going to be an interesting thing to write. And then the update is going to be, how do we want to write this? We're going to say, basically, it works like this. If I think it does. I think it really does simplify the logic. We just put the indices right in there. I gotta sneeze. Okay, so what I think we would do to update the tree is you would say, okay, you've got the start index and end index, and if you're contained in that node, it's kind of hard to say actually how to do this. It's basically if there's any kind of intersection, then you're going to want to recurse on that node. Yeah, something like that. However, you want to recurse on only the intersecting portion. Yeah, man, I got like so. The last time I wrote an interval tree, the last time I did this, it took me so long. I feel like it's always going to take me a while. Like, it's going to be a while before I really get like fast at doing this, because it's kind of tricky. Like, it's kind of involved. I want to say the logic is if the start and end indices are equal, then you're going to modify that node and stop. Right, and you're going to do that on the left and the right indices. Now, we'll say we'll say there's a node pointer root that you're operating on, right? So if your start and end index is exactly what's contained in that root, then you return. If the root is empty, also you're going to return. Although you're not going to return, but you're going to set the modifier. You're going to update the modifier for that root node, and if it's empty, you're going to return. If you're excuse me. Now the tricky thing here is if you're intersecting, but you're not completely on there, then what you're going to want to do is recurse on the left or the right node, depending on what the intersection looks like. So that's kind of the tricky thing, or the tricky thing. And really, you just check the intersection. If you're intersecting on the left node or the right node, then you would recurse. And if you're not completely enveloping that root node, then you recurse on both sides if there's an intersection. And if there's no intersection at all, now here's a question. Yeah, I guess you would do the intersection check before you recurse. You could put that actually like in like the base case, like if you're not intersecting at all, then you just return. I think it simplifies the logic a lot. Yeah, not a lot, but a little bit. That's relatively simple. So we do actually want, yeah. Well, writing in the left and right, or left right, or start index and end index. Writing in those indices simplifies the logic a lot. So we'll do not n, but we'll say begin index, or start index, end index. All right, so we'll do it this way, and we'll say this way. Root new node. Root left, root right. We'll set up shortly. We'll recurse a root. Start index. start index, end index equals end index, and then now we can say f of these other things, and we can say the start index. So the left side is going to keep the same start index, however the ending index, let's say the midpoint, start index plus end index over 2, right? And we'll say this is going to be start index to mid on the left side and mid plus 1 to the end index. And do it that way. And do it that way. That way we have a representative. And then now we can say the update and the retrieve, the logic is a lot simpler. And yeah, so let's do the retrieve logic because that's kind of interesting. So we would say if root start index is less than index and less than or equal to index, and root and index is less than or equal to the root ending index. Whatever we're looking at so far, we're going to do, so say, I don't know, int increment, or we'll just say x equals 0, x plus equals this root modifier. Now, here's the question though. What we're wondering is, do we process? I think we do that. Do it that way. We do the left subtree and the right subtree. So we have a base case, and we'll say there's a left subtree and a right subtree, which we want to operate on. Do this recursively. So there is int left. Yeah. Okay. Int current is 0. We'll say if. Yeah. No. We'll do it that way. That's fine. That's fine. So base cases, we'll say if not root turn 0, and we're gonna say if root start index is less than or equal to index, and index is less than or equal to root, or actually let's do it this way, if start index equals end index, I don't know, I think I know what to do, okay, wait, I don't know, man. Okay, I got it. Okay, int ret is going to be f of root left index f plus f of root right index f, and the reason we do this is that this should terminate immediately, basically, right? So we'd say if not, pretty much if this is not true, then we return 0, right? So we have that index check immediately, and then this is plus, so you don't even need to return ret. You can just do return this whole thing plus the root modifier. There we go, that's what we want, okay. All right. I realize that's a little confusing, but that should retrieve the element correctly. So 2 base cases and then the recursion. And what's going to happen is that when you're not in that range, you'll just return 0, so these won't go anywhere. They'll just sort of stop right there. Yeah. Right. Okay, that's super simple. So we'll write the update code in a moment too. So we want to we have build the tree. We want to run our updates on the tree, and we're going to say for each update, auto update, or just input. We'll just say input, or just query. Each query in the updates int start, and start is query of 0, end is query of 1, and then modifier is query of 2. Right, and that's just kind of the format that's given to us. I believe we could do it that way. So now we have start, end, modifier, and now what we want to do is call the update routine here, update, on the head, and the index is going to be, it's going to be these different values, right? Start, end, and modifier. We update our tree, and that's pretty much it, actually. We don't really need this, do we? It's actually really simple. Right? And now we can, so for each query we run our update, and then we have our return vector, and basically we're going to build the return vector. Oops. For int I equals 0, I is less than length, plus I. I think that's it. Yeah, pretty much. We're going to say ret.pushback retrieve element. Oh, these are also recursive, so I have to remember for query or update to put update in there. And we're going to need some of these here. That is void, I think. Yeah. I don't know if that matters. I don't know. I did that just in case we needed to. I might not need to. Might not matter at all. Anyway, so yeah, retrieve element is going to actually use itself as a parameter. Excuse me. And we're going to retrieve. We're going to use the head node and the index I. Right. So there you go. Okay. Delete head, return ret. Super simple. Okay, or relatively simple. So now we want to update the interval tree, and we said this is going to be relatively straightforward. So base cases, if not root, then return. Right, obviously. Let me say if root start index equals start index, and root end index equals end index, then we're going to root modifier plus equals modifier, and return. Otherwise, we're going to f on root left, operate on the left side with the same start index, end index, modifier f, and on the right side. Now that's not quite what we're going to do. That's not quite right what we're going to do. Int mid equals start index plus end index divided by 2. And we're going to say on the left side we're going to go mid. It has to mirror the same rule we have here. Left side mid, and right side is mid plus 1. Yeah, there we go. Okay, so what that's going to do is, if it should be fine. I think that's the right way to update. We just kind of do it all, right? If we're totally contained, then we stop right there, right? Update the modifier there and stop. If we're not, then we keep recursing on each portion. And you can prove that you're never going to do more than 4, sort of at each level, never do more than 4 recursive calls. So that means you're going to have logarithmic time complexity to update, and also logarithmic time complexity to retrieve, and log n time to do this routine, and something like this ought to do the trick. Now this is like took a lot of time, and we're still not done yet. We're at 40 minutes, 42 minutes. Yeah, it's good to not make it hers also. Private member of node. Is it? Why did we do that? Let's make it public. Make everything public. Keep it simple. Modifier, did I really do that? I did. Nice. Build tree, no matching function. Oh, start index, end index. Okay, right. 0 to length minus 1. Right. Interesting. Non-void lambda 28. Which one? Oh, no kidding. Okay. Right. Yeah, excuse me. My mistake. Oh, I need the root node too for the query. Forgot about that. Yeah, I guess so, huh? Runtime error, nice. Stack Overflow, sweet, perfect. That's what I like to see. That's what I like to see. Great. Perfect. What happened here? I think, no, I don't know. I don't know what happened. I don't know. No kidding. Is it this that's causing the issue? I bet you it's that. No, it's not that. Okay. Deadly signal, stack overflow. Okay. Well, let's see if we can find the stack. Why that's happening. see how we do here. Okay, 1, 2, 3, 4, 5, 6. Let's see how it goes. Check 1 immediately. Okay, so build tree causes stack overflow. Nice. Why? Why is that? Why would that be the case? If they're equal, oh, you know what? You still create a node if they're equal. But I want to say if they're equal to each other, you don't recurse. Maybe that's what I'm missing. Maybe that's it. Maybe it's just that simple. Okay, let's try that. That might be the problem. Okay, wrong, but we didn't overflow this time. That's good. Maybe I could have just. Okay, I probably should realize that that was going to overflow. Not quite sure why I didn't realize that. Really should have known that. Okay, let's try this again. So what's up, chat? We're so close. -2, 0, 2, 2, 0. Okay, so build this tree. We query our updates. Okay. Use 2 test cases too. Let's just see. 1, 3, 2, 2, 4, 3. So are these 0 indexed? I think they are, right? Yeah. Increment. So -2. So these 0, 1, 2. It's -2. Okay. So 2, 2, 2. So let's do this. Let's after each update, let's debug. Let's say temp, push back, retrieve element, head, retrieve element of temp, and we're gonna say for auto x and temp, standard cout space, or just, yeah, we'll do x with a space. Something like this. How does that look? Okay. So the first routine, we got 0, 0, 2, 2, 0, 1, 2, 3, 4, 5, 1, 2, 3, 4, yeah. So, okay, why this first index at 1? Why did this not do what we wanted? When we retrieve that element, why didn't this give us 2, 2, 2? That's a good question. Uh-huh. It's not exactly equal, then return 0. If it is equal, you're going to return left and right plus this modifier. Okay. So this is retrieve element. So it could be two things. It could be the update could be wrong, or the retrieval could be wrong. I would guess the update is wrong, What this ought to do is modify. So the tree that we built is going to look like the following. It's going to have. Man, I'll get wrecked by this problem in an interview. I would get destroyed. It's going to say, okay, start index is 1, so 0, 1, 2, 3. It's 1 and 3. Create a new node, start index, end index. They're not equal to each other, so our mid, we have the left side and the right side split, right? So we operate on the left and the right. So mid of 1, 2, 3 is going to be 2. So 1, 2, and 3, right? So 1, 2, and 3. And that's the left and the right. And so left side will have 1 and 2. This will be created. And the right side, yeah, you'll have 1 and 2. And this time the start index for 1 and 2 is 1. So the left side is 1 and 1, and the right side is 2 and 2. And so you'll create nodes for those two. So 1, 2, and 3, and the one on the right, the third one will just be a 3. Actually, building the tree. I'm sorry, that's wrong. What I just suggested is not correct. A little confusing. I want to say. I want to say it's the retrieval that's not correct, actually. I don't know. I think it's the update and the retrieval. I think the update's not right. I don't know. Confused. Very confused. It's taking a lot of time too. 50 minutes. Ouch. Ouch. The problem seems to be. No, we should be okay. No. Man, this is a little weird. I don't know. What's going on? What's going on here? Why? You know, something's wrong. This should be a 2 on this side. And then also, it looks like this update didn't even take place. Like these other, like there's something's not right. Let's try to figure out why this 2 isn't showing up. Let's start with that. Excuse me. I don't know, man. I don't know. Let's do this. Let's kind of want to build this, print the tree that we built. Can we do that? So we create this root node, right? I want to write a routine that just prints the tree. And no. basically like a level order traversal of the tree. Yeah, I mean, I guess we could do that. So we can say level order traversal is like a queue, I guess. Usually use like, you could use a vector, that works fine. I usually just use it as just a queue. Yeah, okay. We're gonna print it. We're not gonna do a level. Like, we're not gonna get the array. We're just gonna print. So we'll say for q.empty or while. I think while is a little more appropriate. While q is not empty, we're gonna say level, and we're gonna go through yeah, we're gonna say oh, you know what? Yeah, okay, it's a little confusing, but yeah, if root left, then root left modifier. It's actually, this is confusing. Q is not empty. Node n or x equals q dot back. We're gonna q dot pop back. Doesn't really matter how we do this exactly. We're gonna use sort of like a. Oh, actually, no, it does matter. I take it back. This is kind of good practice. These are actually going to be node pointers. So this level, Q is not empty. X equals Q back. This should be Q front. Pop front. We're going to say X left, level push back. X left. You really don't even need to do that. You can do level dot push back X left, level dot push back X right, and then Q equals level. And what you're going to do is C out of X, print all these modifiers, and then print a new line. That'll give you a level order traversal. If not a root modifier. Yeah, something like this. That'll give you a level order traversal of the head, which is what we want. I want to print after each update. I think it's just push into the queue, push and pop. Yeah, okay. Let's see. Tend to get that mixed up. Is it NQ maybe? Let's see. Push, push pop, yeah. Front, back, push pop. What? Oh, excuse me. Oh, no. Whoa, 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 whoa. What just happened? Oh no, hopefully we didn't just get in trouble. Uh-oh. 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 Also, wow, it's taking a while. Alright, we are over an hour. Okay, ouch. Ouch. Okay. We just want the root. Yeah, excuse me. Excuse me. Okay, runtime error, no pointer node. Oh, right. And we just say if not X, continue. Right. We also got a pop. Yeah, that was the, instead of doing the check on each before we push, we could do the check here too. I like that better. Okay, so 0, 0, 0, 0, 0, 0, and then 2 zeros here. Alright, now what does this look like after each, each update? Okay. So that's really interesting. So this is so each of these these are the two children, and there's two children here. So it looks like there's this node and two children, then this has two children, that has two, and this has two children, and this right one has two children. And you would expect actually to be a 2 to not be here. So this is 0 to length minus 1. The 2 wouldn't go there. This is 0 to length minus 1 over 2, which is 5. 4 over 2. So that's 0, 1, 2, and then this is 3, 4. Right? Now, this becomes 3 and 4, and 3 is completely contained in my question is, how does this update? Oh, excuse me. It's the update's supposed to be for if it contains that entire range. We split on these ranges on mid and mid plus 1. So yeah, eventually this ends up being 3 and update on 3. Just thinking if there's like so much better. So much clearer. Oh, that's great. All right. What were we saying? 1, 2, 3. Yes, 1, 2, 3. Right. So 0, 1, 2, 3, 4. The midpoint, excuse me, the midpoint should be 2. So this left node should be 0, 1, 2, and the right node should be 3, 4. So that's 3, that's 4. Right, 4 is outside of 1 through 3. 0, 1, 2. So this should then be 0, 1 is this guy. So this is 0 and 1. So this should have a 2. And this is actually 2. This is 0, 1, 2. This becomes 0, 1. This becomes 2 and 2. Why does this not have 1 though? Why does that? What happened there? I think it's the update that's incorrect then. It must be. Oh, it's how I built the tree, I think. No. These indices are equal. Left and right are just null pointers. No, that's fine. What is wrong? I don't get it. I don't understand. I'm very confused. Yeah. I'm utterly confused. I don't get it. I don't get it. Doesn't make a lot of sense, man. This doesn't make a lot of sense. So, let's do this. Because there's not too many nodes to work with here, right? There's only like 9 of them. 1, 3, plus 4, 7. Yeah, no, that was exactly correct. 9 nodes, okay. I have to admit I'm very confused, but this shouldn't be too bad. Should be able to figure this out. I don't know. I don't know what I did wrong. I don't see it. I mean, I don't doubt I did something wrong, of course, right? But I don't know what's going on here. Okay, start index 1, 3, and this is for the update. Okay, no, we want the root start index, right? Oh, you know what? No, yeah, what? We do all of it. Yeah, let's try that. Okay. This is what we want. So start index, end index, modifier, and well, the modifier is always the same. We don't really care about that. Basically, we want to see what happens in each of these cases. So our start index and end index is initially 1 and 3. The node is 0 to 4. Modifier is 0, right? So we don't do anything there. Then we have start index 1 and end index 2. Right, that's the left side. We said that before. 0 and 2, right? So we shouldn't modify that. Then we say start index 1, end index 1. Node start index is 0, end index is 0, 1. I think we said that, right? We said what this thing looks like here. One, 2, 3, 4, right? So 1, 2, 3. Node start index 0, 0. So that's kind of interesting, right? So that one straight down on the left shouldn't be modified. However, the one on the right of that should be, which is node start index 0, 0, end index. So start index 2, end index 1. Now what happened there? Why? Now that's not correct. That should just skip, right? That's what you're calling the update. Oh, that's really confusing. That just shouldn't matter. Oh yeah, so I guess that is one base case. It's if start index is greater than end index, they just return as well. I didn't really think about that. I don't think that matters, but at least handles that case. 0, 4, 1, 2, 0, 2 doesn't quite match. 1, 1, 0, 1 still doesn't quite match. 1, 1 doesn't match 0, 0. 2, 2 does match 2, 2. And then it should update there, right? So, oh, well, what about 1, 1? What happened to 1, 1? 1, 1, 0, 1, and then 1, 1, 0, 0. There should have been a 1, 1, 1, 1. That just didn't happen here. That's exactly what we're missing. Why didn't that happen? Why wasn't there a 1, 1, 1, 1? It's a lot of ones, but yeah, that's the question. What happened to my 1111? Where did it go? Why is that not happening? Hello? There's the left side, there's a 0 and a 1. Excuse me. I think because the end index, so confusing. Yeah, I'm just confused. I'm just confused. No, man. What is going on here? I think I need a picture. I think I need a picture to figure out what's happening. It's definitely really confusing to me. I kind of feel like this should never happen. What are we doing? What are we doing? You could actually do it this way. Instead of using these values, you could just say this. Just do it this way. Say the start index. Basically, if the root node that is contained, yeah, so is less than this guy, and the ending part is less than or equal to the end index. You do it this way, I think it's better. It's a lot simpler. Yeah, okay. Why does it have to be so difficult? Why make this so difficult? Why? Why make this so difficult? It's kind of funny, these parameters just get passed through. Okay. Oh, it's correct too. Now it's correct. All right. That's great. I'm glad. Glad I only had to spend like 20-30 minutes trying to debug this to figure out what's wrong. Wrote so much extra code to debug this. And it's correct. And we're done. Nice. Okay. Excuse me. Oh. Oh no. Bah humbug. Okay. If I hit that reset to default button, I would be so sad. I have to rewrite all that. Alright, how do we do? How do we do? Okay, it looks correct. Let's try another test case. The logic is so simple, but it's just I made it so much more complicated than it needed to be. How did we do? Did we TLE? Oh no, we got it. Okay. Should we just go? Yeah, we'll just go for it. Hey, got there. Sweet. That took forever, man. That took so long. I might come back to this later. And look at this efficiency. It's like so much less efficient than everyone else's solutions. So, yeah. Basically, right. The node class is super simple. And you build the tree. It's relatively simple as well. The update logic should be really simple. Again, relatively speaking, it is. And tree element logic is simple. Right, all you have to do is check for sort of containment, that the index is contained in the node's range, and then also that the modifiers that you're updating, the range contained within that modifier is contained in the larger range that you're looking at, and then you don't recurse once you do that. You don't continue, and then all right, you build the tree, process all the update queries, and then build the return vector out of retrieving all the elements, and then dump the tree, delete the tree, and return your vector at the end. So, I mean, that's all well and good. The question is, a couple things. This could be done a lot faster than I did it just now, like way faster. That's one thing. Second thing is this could be done way faster. This also could be implemented differently to be more efficient as well. So not have so many recursive calls. You could probably build this in a single array and even do it iteratively rather than your update and your retrieval. Actually, the retrieval could be really simple. The update could be iterative, and the retrieval is actually, like, let's just say very efficient, because it's basically just taking a chunk of an array, a consecutive subsequence of an array. The update could be also iterative and really extremely efficient, and the tree also, building the tree could be basically constant time. So you can make this a lot more efficient, a lot faster, and a lot better on memory by implementing this in an array rather than as like a tree structure. So I think tomorrow we'll look at that, get into that, take a look at it, see how it goes. But yeah, that's pretty good. That's pretty good. So yeah, that took forever though. That took an hour and a half. That's a lot of time, man. So that's interval tree. That's an implementation of it. I have implemented interval trees in the past. However, I still kind of struggle with it, as you can tell, as you see. So I get better at it over time. I will improve over time. But for now, we'll leave it as such. So yeah, thank you all for watching. I'll talk to you soon. Have a good rest of your day. I think that'll probably be it for tonight. Maybe, I don't know. Actually, I can keep going. I think I'll probably do another problem. Maybe one. If it's quick, I'll do two, but possibly two. Probably just one, if that. So I won't come back to this. I'll come back to this tomorrow. And yeah, so thank you for watching, and I'll talk to you soon. Take care.